Yeah, welcome. So today we'll talk about the Quartic rule. So the idea here is that when we look at a graph, we'll be able to find a rule given a number of points, so we can use that as information. But first of all, let's discuss the x-intercept forms for a Quartic. Very similar to the previous polynomials, except you can have 4 intercepts since you do have an order of 4 for this polynomial. So you can have dilation of A, and you're going to have x minus a certain constant in four different brackets. You can have 3 x-intercepts as well, so you don't always need to have 4 at maximum. But the idea here is that one of your brackets over here is going to be squared. What does that mean? Does it just cut through the x-axis? Not necessarily. Remember back in cubics, if you've got a bracket to the power of 2, this means that you're going to have a turning point, or I like to call it a parabolic kind of x-intercept, because it does look very similar to a parabola, but it's not always symmetrical, remember? So this is why we say there's a turning point at that x-intercept. What about when you have 2 x-intercepts? So one of your brackets is to the power of 3, the other one's to the power of 1. So there's a hidden 1 here. So we still have a Quartic expression altogether, but when it's to the power of 3, this means that you're going to have a stationary point of inflection at m over here. So it's referring to the x-intercept that you grab from the bracket that is to the power of 3. Now, you can also have 2 x-intercepts if both your brackets are to the power of 2. So if they are both to the power of 2, this means that they both have the parabolic kind of x-intercept, or in other words, they're going to have a turning point at that x-intercept. Alright, let's have a look at the one down here. So we want to find a rule of the Quartic over here. Now, if we use the x-intercept forms, it's quite simple. So how many do we have here? We've got 1, 2, and 3 intercepts. So we're going to have y equal to some dilation. And we got x minus, now we've got an intercept at 2, 0 over here. So I'm going to say x minus 2. It's going to be one of the brackets. It cuts through the x-axis, so this is going to be to the power of 1. Cuts through the origin, so this is x minus 0. But of course, that's just x, so I'm just going to leave it as x. And going for the last one here, see this turning point here, or this parabolic kind of shape. So when you have an x-intercept at negative 3, 0, you can have x plus 3, and this is in order of 2, because we know that there's a turning point there. So just cleaning this up a little bit, we're going to have ax, x minus 2, times x plus 3 squared. Okay, so where do we move here? So to find a rule, we only want y's and x's, but we don't have an a here. So we have to use some bit of information over here to find out what a is. So if we have a coordinate, we can sub in values of x and y to be left over with a. So how about we try and sub in 1, 9 here? So when y is equal to 9, x is equal to 1. So we have a times 1, which is just, well, a. 1 minus 2, 1 plus 3, squared. Okay, so this means over here we're going to have negative 1 here, 4 squared, so we have negative 16 altogether. Sorry, not negative 16, we have, oh yes we do, sorry, negative 16a. So this means that our a value here must be negative 9 on 16. So our rule altogether is just going to be subbing this back into here, and that would give us y equal to negative 9 on 16 x minus 2, x plus 3 squared. Over here. Alright, what about over here? So we have another Quartic, and we know that because we're going to have one intercept here, and there's a stationary point of inflection at our intercept. So this means that there has to be a power of 3 for this x-intercept over here. So let's work with this one first, the simpler one. You have x plus 3. Oh, so we can't forget about our dilation. We're going to remember to put the a value over here. And where we have 2, 0, we're going to have x minus 2. But if it's a sploid, this means I'm going to have a cube over there. Okay, so again, it's just about finding your dilation over here. And you can find what it is by using any coordinate, and that includes the y-intercepts that were given. So, subbing in 0, negative 12, we're going to get negative 12 equal to a x plus, sorry, not x, the x is now 0. So we're going to have 3 times negative 2 cubed. And this one over here evaluates to negative 8. Negative 8 times 3 is negative 24. So this line over here, negative 12, is equal to negative 24a. So a has to be 2. And so we just sub a back in to find our rule. That's about it. Alright. You might have noticed so far, just add in, that the a value here also dictates if it's a positive or negative cubic. Quartic. So it doesn't really matter if you identify whether this is an upright quartic or upside down one at the moment. When you calculate the value of a, it'll always tell you what it is. Okay, so for this one down here, negative quartic here, something funny is happening. Looks like an M, so maybe it's a simple one. Let's have a look. Got a turning point over here. So if we have a turning point at 0, 0 and this intercept at the same time, we're going to have x minus 0, but remember x minus 0 is just x, but we have to square this because we have a turning point there. We're also going to have an x-intercept at 4, 0. X minus 4 is a turning point as well. So we give it that little bit of a parabolic spin by saying we're going to square that linear term. Of course, our dilation of A, all of this is equal to y. Alright, so to find A, just use the leftover coordinate here. Summing in 1, negative 9 gives us negative 9 equal to a x squared. So this means that x over here, we just have 1 squared. Then we have 1 minus 4, 4 squared. So we just have negative 3 squared here. So this means we're going to have 9a equal to 9. So a is equal to negative 1. Subbing this back in to our original equation up here gives us our rule. And that's about it for sketching quartics. Hope you enjoyed that.